spin dynamics. So basically, what we are going to discuss today is effects of time-dependent magnetic field. The Hamiltonian which I'm going to consider today, H, which is minus M dot magnetic field, which depends on time. There are several areas where this problem appears. It's of course related to the dynamical effects in magnets, localized or itinerant. There is experimental technique to measure the spin precession, and we will see that what kind of information it gives to us. I will also introduce you to dynamical susceptibility. We will see that in the simplest case of spin precession, we can consider it as a sort of optical magnets. So this dynamical measurement provides you information about some spectral properties of excitations. Monday we continue discussing ferromagnets with a microscopical model, and we will see how this dynamical susceptibility can be found in the localized local ferromagnets. Yet another application of what I'm going to tell you today is related to quantum computing. It's a dynamic of qubit. You know, qubit is a quantum bit. In most simplistic way, one can consider it as a two-level system. Spin 1/2. There are several ways to prepare two-level system. It's not necessary to be spin, but manipulation with a qubit assumes that you perform some unitary operation with this, and also perform some time-dependent operation with spin. So we need to see what happens if your spin is subject to time-dependent magnetic field. Okay, without losing generality, I will split my time-dependent magnetic field in a way that there is a component which is time-independent, and I will choose my z-axis along with this time-independent component, and plus some time-dependent component which is in perpendicular to z direction. Then I will be talking about magnetization, M. And last time we discussed for the quantum problem that magnetization is related to total momentum. I can still write J, but for the sake of simplicity, I will consider from the very beginning that my orbital model. I remind you that J is S plus L, well, operator. And for the sake of today's lecture, I will consider L equal to 0, therefore J is equal to S, G factor is equal to 2, so the magnetization is G mu Bohr S. And I remind you that the Bohr magneton is modulus E H bar divided by 2 MC. Again, if I'm talking about ferromagnet, I'm talking about macroscopical quantity, which is magnetization. So in principle, everything what I'm saying would be that M is G mu Bohr, sum over all sides of the magnet Si. So everywhere we can put summation and say that this is macroscopic parameter. But again, for the sake of the derivation, it's sufficient for me to say that I have connection between magnetization and spin, consider like spin, so I will need index of summation. As an exercise, you can repeat everything what I'm saying here, assuming that you have in mind some piece of magnet, there are some sides, there are some spins sitting here and there, and you take a summation of all positions of spins. What I consider saying that my spin or magnetization is large macroscopic quantity, I will again consider this magnetization on the sphere as we did for semi-classical approach. And the first step which I'm going to make is to write down and derive a very simple equation which describes the dynamics of the magnetization vector when you apply to it time-dependent magnetic field. Okay, I start with reminding you of the commutation relations for spin, namely S alpha, S beta. The commutator is equal to I epsilon alpha beta gamma S gamma. Okay, this is a spin algebra, which is valid for spin 1/2 for any arbitrary spin. Then I will start with equation of motion for the operator S alpha. Again, I will omit hat everywhere, assuming that I have operator, so I am writing Heisenberg equation of motion. So the Heisenberg equation of motion says that this is I divided by h bar, and I have a commutator h with S alpha. So this is equation, and dot means that this is ds alpha over dt. So I take the component alpha, it's here and there, and take the Hamiltonian written down here, and then we proceed with the derivation of the equation. So S dot alpha is equal to I over h bar sine minus. I have a commutator. Let me write down the Hamiltonian. So the Hamiltonian is minus g mu bar. As I said, I will write the scalar product is as m beta s beta and s alpha. So I remind you Einstein notations. When I'm writing two repeating indices, it assumes summation of these repeating indices. And what is wrong here? This is h beta s beta. Okay, so this, the right hand side is equal to minus I over h bar g mu bar h beta, and we have a commutator s beta s alpha. Now the commutator s beta s alpha is in form equal to minus I over h bar g mu bar h beta epsilon beta alpha gamma, let me use lambda s lambda. Okay, and there is some way to I to minus I gives me 1. So this is g mu bar divided by h bar, h beta, and now I will flip these two indexes. But flipping two indexes means my Levi with the tensor alpha epsilon beta alpha lambda is equal to minus epsilon alpha beta lambda. So this is minus epsilon alpha beta lambda s lambda. And again, I will write it in the form as plus g mu bar over h bar epsilon alpha lambda beta s lambda h eta. Okay, I again flip these two indices. So this is minus epsilon alpha lambda beta. So what we see here, this is G over mu bar divided by H bar, and this is a component over S times H alpha component. Okay, let me see, I did not make a mistake. I did not. As a result, if I multiply the right-hand side of this equation and left-hand side to G mu bar and to G mu bar, I think that G mu bar is incorporated in monetization, so I can write down that M dot is equal to G mu bar over H bar, and I have a vector product M times H. Okay, I will denote it as gamma. So the coupling constant gamma, which is G mu bar divided by H bar, it is equal to, if I plug in 2 times E mod H, 2 MC H bar cancels out, factor 2 cancels out, so this is E divided by MC. So I got equation which in the literature called gyroscope equation. And now I'm going to solve it under certain approximation, considering some configuration of the magnetic field. So this is a gyroscope equation. Good. Let me start considering some particular problem. By the way, if I take summation over I, you can check it doing this derivation, you will end up with the very same equation. Okay. I did not forget anything. So let's consider the problem when the magnetic field HT is equal to H naught EZ plus constant H1 times cosine omega t times EX. So this is the problem I'm going to solve. So this is axis which is parallel H naught. Then you have oscillating field with a small amplitude. I will assume that, H is much smaller than H naught. It will help me to do something. So this is the oscillating field along the direction x, and I draw the sphere with a radius equal to magnetization M naught. Okay, so let's write down this equation component by component. So the right-hand side is the product. So it's a gamma times determinant Ex, Ey, Ez. Then I have Mx. I will assume that my magnetization vector Mt has the following components: Mx, My, and so this is Mx, My, Mx, and I will also assume that value m normal, so this is m normal minus mz. I will denote with the small letters small component, as with the capital letters big component. So in this sense, mz in this notation is this small part. This is m node minus mz. Okay, so this is mx, my, m node minus mz, and then I have a field which is h. You remember that this is h1 t, so this is h1, 0, h node. So this is the right hand side. If I open, if I write down the determinant, it is equal to ex times this determinant. So this is my times h node plus ey, or in direction y. Then I have a determinant, this m node minus mz times h1 minus mx times h node, and plus ez times minus my times h1. So h1 depends on time, h1 depends on time. Okay, good. I will keep this central equation for 10 minutes. So now I'm ready to write down my equation component by component. Of course, everything is multiplied by gamma. So, dmx over dt. This is this component. So this is equal to gamma h node times m1. Then dmy over dt is equal to minus gamma h node mx plus gamma m node minus mz times h1, and dmz over dt is equal to minus gamma my h1. So this is difference. So this is system of three differential equations, and although the system looks like linear, it is actually not, because the components mx and y and mz are connected with equality mx squared plus my squared plus m node minus mz squared is equal to m node squared. This is a sphere. Good. The non-mandatory homework for you. First of all, using the same method which I used, namely writing down equation of motion, shows that equation of motion for m squared is equal to 0. You compute the commutator over m squared with the Hamiltonian h and show the right hand side is 0. Which means that the total length of my monetization vector is conserved, and my monetization vector indeed lives on a sphere. And what I do is legitimate. Now, I have a system of complicated equations. Let me simplify under some assumptions. And these are the assumptions. First of all, I assume that h1 is much smaller, so the modulus is H1, than H naught. Assumption number one. Assumption number two, I assume that M naught, that M alpha, where alpha is x, y, z, is much smaller than M naught. Precisely like I plotted on the blackboard. Under these two assumptions, the first equation remains intact because it contains one big quantity, one small quantity. In the second equation, this term is intact. This term I drop because it contains quadratic smallness mz and h1. In this equation, actually, I should drop everything because it contains my and h1, and therefore the right-hand side is 0. So this is a system of simplified or linearized equations. Let me rewrite it again. So, I will introduce new notation. So you remember that gamma is modulus E over MC. Therefore, gamma times H naught is modulus E H naught divided by MC, and you recognize that this is Larmor frequency. Larmor. I will denote it as omega naught. So therefore, the first equation reads dmx over dt is omega naught times my. The second equation reads dmy over dt is minus omega naught mx plus gamma m naught times h1 t, and the third equation reads dmz over dt is equal to 0. So these are linearized equations. So, first of all, let's look at the equation number 3. It tells us that mz is constant. In principle, from here, you get that mz being constant is a function of mx and my, and this equation, this one, under the condition that mz is constant, defines some trajectory on the sphere. We will see that this trajectory is just a circle in few minutes. So, trajectory. Now, let's look at this pair of equations. So you see that I had a condition for the longitudinal part. Longitudinal means this is a part parallel EZ. And now let me write the equation for the transverse part. Of course, in order to do it, to write down closed equation, for example, for mx, let me differentiate the equation number 1 with respect to time 1 d2 over dt squared mx is equal to omega naught d over dt m1. But for the second equation, I can plug it in. I will continue here. So this is omega naught times minus omega naught mx plus gamma m naught h1 t. Therefore, my equation is mx double dot plus omega naught square mx is equal to gamma omega naught m naught h1 t. So what we get is classical harmonic oscillator. Namely, this is the oscillator, of course, and this is external force, which I will denote as Ft in the right-hand side of your harmonic oscillator. So basically, this is a driven harmonic oscillator. Therefore, what we are getting physically is that your magnetization vector will precess with respect to z-axis with a frequency equal to Laplace frequency. This is a precession. Good. Let's now write down a solution of this problem for this particular choice. I would like to complete solution of the problem. So solution of the M magnetization Mx is equal to, first of all, I need to write solution of homogeneous equation. Solution of the homogeneous equation is A times cosine omega naught t plus B times sinus omega naught t. I have a second order linear differential equation, therefore it contains two independent constants A and B. This is solution of homogeneous equation. And then I have a solution, particular solution, which is the solution corresponding to the right-hand side of equation. So homogeneous part of magnetization satisfies the equation with 0 in the right-hand side. And in order to find a particular solution with this type of the external force, I will be looking for it as a C times cosine omega t. If I assume that the driving force, omega of the driving force, is not equal to omega naught. The case where omega is equal to omega naught, I leave to consider to you. Just take your favorite book of classical mechanics and see what happens if you drive your harmonic oscillator with a frequency which is exactly equal to the frequency of the oscillator. I will consider the case where the frequency is different. Then I will want to look for a solution of this equation in this form. If I plug it in, I get constant C times omega naught square minus omega square is equal to gamma omega naught m naught h1, and therefore C is equal to gamma omega naught m naught h1 divided by omega naught square minus omega square. So the total solution of my equation mx t is equal to mx homogeneous plus m tilde t. Good. And then you apply some initial conditions. This is what you have in your homework. And by applying initial condition, you need to have two initial conditions. You identify constants A and B, because constant C is all you know. So this is how you solve problem completely. Good. Now, I'm coming to discussion of very important point of the susceptibility, dynamical susceptibility of the system. Let's define it and again compute for linearized equation, which is the harmonic oscillator. Once again, I'm dealing with transverse component. Longitudinal component is preserved, therefore I have a cut, so everything is happening in the z-plane defined by condition and z is constant, but in z plane you have a circle, your orbit is circle, so your magnetization is just precessing like that with respect to z-axis. Okay, good. General definition of the susceptibility. Now I'm talking about something which corresponds to the response to the magnetic field. So I'm not talking about the homogeneous solution of differential equation. I'm saying that if you apply to the system some time-dependent magnetic field, so you have a response, namely the magnetization at the time moment t, and in the coordinate point r, is equal to integral over dr prime, integral from minus infinity to infinity dt prime, and then I have some kernel which is chi r minus r prime, t minus t prime, and I have external magnetic field h at t prime. When we discuss diamagnetism, paramagnetism, we consider susceptibility as a proportionality coefficient between applied magnetic field and magnetization. Here it's more general. Namely, you apply magnetic field locally at some coordinate point r prime and the time moment t prime, and you are looking for response to this field at the coordinate point r and time moment t. Again, what I'm doing is linear response theory, because my magnetization is proportional to the magnetic field. However, this connection is non-local, and it assumes some retardation. Therefore, you apply something in the past, and you see the response in the future. Okay, the problem now is how to compute this susceptibility for that particular model of the described spin dynamics. And let me show you the method, how to do it. And this method is related to finding the green function of linear differential equation. What I'm going to show you in the next 10 minutes is how to construct green function of the linear differential equation and connect it with the susceptibility, which what I'm looking for. We have our equation d over dt squared mx plus omega naught squared mx is equal to ft, some external force. Okay, let me define the differential operator L, which is d over dt squared plus omega naught squared. Then my equation, this is a differential operator, reads Lt acting on my magnetization Mx is equal to Ft. Okay, for the solution of this equation, I'm looking for the dependence of magnetization and functions of T, and I have a driven system applying external force. The formal solution of this equation is Mx is equal to L minus 1 T times Ft. So I need to construct the operator inverse to the linear differential operator, L minus 1. I can rewrite this equation as Mx t is equal to integral from minus infinity to infinity dt prime. I will put delta function t minus t prime, because this is identity, and then I write L t prime minus 1 times f t prime. If I take this integral, then I get this condition. On the other hand, following the same procedure as before, by the definition, I'm writing as integral from minus infinity to infinity dt prime, some green function g t minus t prime f t prime. By comparing these two equations, I can write down that L minus 1 t prime times delta t minus t prime is equal to green function t minus t prime. This is the function which I'm looking for, or if I apply inverse operator again, I can write down that Lt prime acting on the green function t minus t prime is equal to delta function t minus t. So what it says, that the green function satisfies the same sort of differential equation. Remember, we have L times mx is equal to ft, where instead of external force, you have delta function. Delta function is a Dirac differential function. So this is the equation for the object Gu, which is green function of the linear differential equation. Why this method is so powerful? Because if we know the green function, whatever external force we know the particular solution. For example, here I consider very simple form. Suppose I have crazy form of the external force, consisting of Legendre polynomials or whatever. I don't know how to solve this differential equation because I don't know in what kind of class of functions to look for the particular solution. However, if I know the green function of this differential equation, I can plug it into this integral, compute the integral, and find a particular solution for my problem. Okay, let's now solve this differential equation and find out the green function for the harmonic oscillator. Classical harmonic oscillator. Okay? Good. In order to do it, as you learned it in the course of mathematical technique, we apply Fourier transformation. Because the differential equation, we have a linear differential operator, after we apply Fourier transformation, we'll transform the differential equation into algebraic equation. So we Fourier transform this equation, get algebraic equation, we solve it, and we take inverse Fourier transform and get the green function as a function of time. So this is the way how to construct the green function for this particular problem of harmonic oscillator. Okay, Fourier transform. G omega is equal to integral from minus infinity to infinity d tau. I denote tau as t minus t prime. So I have e to the power I omega tau g tau. Because you see that the green function depends on the difference of time and t prime. So the inverse Fourier transform g tau is defined as integral from minus infinity to infinity d omega over 2 pi e to the power minus I omega tau g omega. And let me also define the Fourier transform of the delta function. So the delta function we know is just integral d omega over 2 pi minus infinity to infinity I minus I omega tau. This is one of the representation of delta function. If you take a Fourier of the delta function, you get 1. Good. Okay. Now we have everything and we plug it into the differential equation. The left-hand side is d over dt prime plus omega naught square, which acts on the integral from minus infinity to infinity d omega over 2 pi e to the power minus I omega tau G omega. And the right-hand side reads that this is integral from minus infinity to infinity d omega over 2 pi e to the power minus I omega tau. Okay, this is the equation. You see that only tau depends on t minus t prime, nothing else. Therefore, I can apply this differential operator to the exponent, and what I get, that omega naught squared minus omega squared, I equate two integrals. I equate two terms in front of the exponent, in the left-hand side and in the right-hand side. G omega is equal to 1. Therefore, G omega is equal to 1 divided by omega naught squared minus omega squared. So this is how I found the green function of my linear differential equation. Now, in order to find the green function as a function of time, I need to take a Fourier transform of this function. And here I come to very important and physical question. Because the form which I wrote here is still not fully defined. What I'm saying, I'm going to connect susceptibility with a green function, which also depends t minus t prime, and this is tau. So I have to consider two situations, tau positive and tau negative. So if tau is positive, which means t is larger than t prime, or t prime is smaller than t, therefore I did something at the time moment t prime before t, and I see a response. So this should be some green function g tau. However, if tau is negative, namely time is less than t prime, it means that I did something in the future, and I see how this affects my present. And of course, our future cannot influence our present. We have so-called causality, so therefore in this situation, green function tau should be equal to 0. So how to update my definition of the green function such a way that we have this causality property. Causality. I show you that in order to do it, it's sufficient to shift omega naught square minus omega plus I delta square. Remember we discussed similar thing when we discussed adiabatic switching of the direction, and take delta 0 plus. So delta is infinitesimally small and positive. Let me show that this is the correct way to define what I will call retarded green function. So this is effect of retardation. And retardation means that only past is influencing our present. The future doesn't influence our present at all. In principle, I can imagine, like in science fiction, completely opposite situation, when past doesn't influence our present at all, and only future influences our present. It will mean that the property of the green function are completely different, namely I involve sine of tau, and it will also mean that I need to replace it to minus I delta. And such a green function is called advanced. So this is retardation, and the opposite green function is called advanced. I'm not going to dwell into this detail. For me, it's sufficient to write retarded green function, because anyway, a retarded and advanced green function are connected by complex conjugation. Doing more beyond my course, if I'm teaching you the main body perturbation theory technique using finite diagrammatic and green functions. I will introduce green functions for main body problem, which at the end of the day will not be a solution of some linear differential equation. However, I can visualize my green functions with certain lines and proceed with a computation of the main body theory using such kind of green functions. But retarded and advanced green functions are in the core of any diagrammatics. So, if we have GR tau positive, this is integral from minus infinity to infinity d omega over 2i e to the power minus I omega tau, and I wrote here, let me write it as a minus, and here omega minus omega plus I delta square minus omega naught square. I'm going to compute this integral using a contour integration. So if tau, there are two poles of this function. And as I said, this is omega naught, this is minus omega naught, and what I did, I shifted these two poles a little bit in the lower half plane. If I compute this integral, I need to close the contour. If tau is positive, this is a convex plane over omega. So this is real part of omega, this is imaginary part of omega, and this is real part of omega. So, in which side should I complete my contour? So if tau is positive, I have minus I omega prime plus I omega double prime tau, which is minus I omega prime tau plus omega double prime tau. So tau is positive. Therefore, in order to be able to use Jordan lamp and provide the condition that the integral on the semicircle is vanishing, I need to close my contour such a way that omega double prime is negative. Because in this situation, I have exponent at large tau, omega double prime tau, and the integral of the semicircle vanishing. I cannot close my contour in the upper half plane because in that situation, the integral of a semicircle will be exponentially large. This is what happens for tau positive. However, if I have tau negative, then I will do opposite. Using the same arguments, I will need to close my contour in the upper half plane. But in the upper half plane, there is no pose of my green function. Therefore, I am automatically getting through the contour integral that tau is 0. So, indeed, I just proved to you that in order to satisfy this causality condition, what one needs to do is to add infinitesimally small imaginary part to the frequency, and this will give you a retarded green function. In a few minutes, we will see that in the system of dissipation, namely if you have some relaxation processes, one needs to do nothing. As soon as you consider some friction in the system or some dissipation, you will correctly get retarded effects, and we will associate with this delta, which is going to be finite, with some inverse relaxation types. Delta has a dimension of frequency, so the inverse delta has a dimension of time. Okay, now I showed you that with these definitions I get correct retarded green function, and let's now compute this integral. Okay? I hope you understand what I'm doing, and I know with Professor Selita you did many quantum integrals, so you should understand how to work in the complex plane. So this is minus integral from minus infinity to infinity, d omega over 2 pi. Let me write it as omega minus omega naught plus I delta minus omega plus omega naught plus I delta e to the power minus I omega tau. And if I write now collect terms and write this in the bracket, I should divide it by 2 omega naught. Everything is correct. So I have minus 1 over 2 pi, 1 over 2 omega naught, and now I close my contour in the lower half plane. Again, retarded green function by the definition doesn't have any poles in the upper half plane. This is called upper, and this is lower half plane of omega. So it has poles in the lower half plane. So therefore, following the theorem of residues, this integral is equal to residual, and residual is a coefficient in front of the term in level in lower expansion, which is 1 over omega. So therefore, first of all, this term, it's minus 2 pi I times residual. Minus because my integral is a clockwise. And you remember the sign is plus if the contour is going counterclockwise, and minus if it goes clockwise. So the residual is equal to 1, at the point omega is equal to omega naught. Therefore, I have e to the power minus I omega naught tau divide, this is this. So then I have minus times minus plus 2 pi I, and the function at residual is e to the power I omega naught tau. So therefore, you know what, I would probably do slightly better. Let me do it slightly better. So here, omega is equal to omega naught minus I delta. This is this. So this is minus I tau, omega naught minus I delta. And this is minus omega naught minus I delta. Minus I tau, minus omega naught minus I delta. Okay, now it's better. First of all, I cancel out 2 pi. Yes. Did I make mistake with sign? No, I did not. Let's see. GR at positive tau is equal to minus and minus plus, but it's 2 omega naught I. I can take e to the power minus delta tau, and what remains in the brackets is e to the power minus I omega naught tau minus I'm a bit no, I think it's correct. It's not minus but plus, because I have a minus and minus, and I got plus. Plus I omega naught tau. So now sign is also correct. Again, minus and minus gives me plus. I have I, which is written here. I have e to the power minus delta tau, and I have two remaining exponents. So what I will do, I will multiply it by I and divide it by I. So times I divided by I squared gives me minus, and I flip these two terms. So GR tau positive is equal to e to the power I omega naught tau minus e to the power minus I omega naught tau divided by 2I, and I have omega naught, and I have e to the power minus delta. Good. So the green function, we recognize that this is sinus omega naught tau divided by omega naught e to the power minus delta tau, and as I said, if we want to extend it to all taus, I need to write the theta function tau, and theta function is the Heaviside function. It is equal to 1 if the argument is positive, and it is equal to 0 if argument is negative. So this is the definition of the theta function. So, okay, in principle, now I can take the limit delta goes to 0, and therefore if the limit delta goes to 0 is taken, this factor is equal to 1. Good. So, what did we get? We get that particular solution, magnetization x at the moment tau, is equal to integral from minus infinity to infinity dt prime, retarded Green function t minus t prime, and then I have gamma omega naught m naught h1 t. So I see that my magnetization is proportional to applied magnetic field. Therefore, all what comes out here is the susceptibility. My susceptibility Xx, susceptibility is tensor. Now we have a completely isotropic situation. So the tensor can be written in the principal axis. So it contains xx, yy as the z component, and they are all equal, actually. T minus t prime is equal to gamma omega naught m naught times retarded Green function t minus t. Okay? Are you still with me? Or you are doing something else?
Yeah.
Good. So, which means that if I take Fourier transform, chi xx as a function of omega is equal to gamma omega naught m naught, Green function retarded as omega. However, by doing what I did, namely taking my pole and moving them slightly in the lower half plane, this is what was done here, means that my Green function and susceptibility are complex, analytical complex function. So the Green function, retarded Green function, is analytic in the upper half plane. Good. But this is a complex function. It satisfies Cauchy conditions. And let me write down how this real and imaginary part look like. So, once again, G R omega is equal to 1 over 2 omega naught, actually minus, times 1 over omega minus omega naught plus d delta, minus 1 over omega plus omega naught plus d delta. You know, if you have expression 1 over x plus I delta, then you have a principal value of 1 over x minus I pi delta function x. So, therefore, of this green function. I hope that you learned it from your calculus course, or you know it from your university, because students who got bachelor, to say nothing about master, should know what is the principal value and what is the delta function. So imaginary part of the retarded green function, omega is equal to, it's equal to pi over 2 omega naught, and I have a delta function omega minus omega naught minus delta function omega plus omega naught. And real part of the retarded green function is equal to minus principal value over omega squared minus omega naught squared. First of all, we see that the real part minus omega is even function. Its real part g r omega, and we see that imaginary part is even odd function. So your imaginary part, if we plot it, consists of 2 delta function of x. So this is omega naught, 1 delta function, and you have. So basically, by measuring this dynamical susceptibility, you measure precisely the frequency of precession. Moreover, we will see that measuring that we can relate susceptibility to some spin-spin correlation function, the same way as we related polarizability to some density correlation function. I told you about this briefly. So measurement of imaginary part of the susceptibility provides you information about the frequency or about the spectrum. So, and this is basically what neutron experiments do. You measure imaginary part of susceptibility through the cross-section of neutron scattering. You can measure it as a function of Q and omega, and it gives you direct access to the excitations, magnetic excitations, but not only in your system. You can measure with neutrons photons, you can measure with neutron magnets. Good. And by knowing that, for example, it was very important in the time of high temperature superconductivity, when it was discovered to measure photon spectrums of these complicated materials and see whether photons are responsible for this or not. And it was shown that photons have nothing to do with the high temperature superconductivity of cuprates. Good. So, I spent 1 hour for describing the solution of gyroscope equation and construction of the green function. Let's spend remaining half an hour to discuss problem with dissipation. So, blow equations. Although the macroscopic theory, microscopic derivation of blow equations for some particular situation is enough complicated because, as we see, as I would mention, it has different meanings for transverse and longitudinal components. Let's phenomenologically add some relaxation to your equation. What I'm saying is that let's write that dmz over dt. I'm restoring the equation, which is gamma m times h z component. I will by hand add some relaxation mz over t1 to it, and the same way for the transverse component d in x or y over dt. It is gamma m times h x or y minus m x or y over T2. So you see that the problem of precession actually split in two parts. First of all, you have something related to the component along the edges, and everything else is related to the isotropy in the plane, where you, in the absence of relaxation, you have just precession. So with this equation, the meaning is simple. It's just like adding friction to your harmonic oscillator, and this is what I'm going to do right away. With the first equation, it's a bit more complicated because this is kinetics. If I do the same linearized trick, I write down the dmz over dt, which in the absence of the relaxation was equal to 0, and mz was conserved. Now this is minus mz over t1. So t1 is longitudinal relaxation time, and this is transverse. Let's look at this equation. This differential equation has very simple solution. So mz is equal to c times e to the power minus t over t1. And if we set the problem that you put your magnetization vector at the equator at time equal to 0, so you put your magnetization vector like that, and then you see what happens with it at larger times. If at t equal to 0, your m node minus mz is equal to 0, which means that mz t equal to 0 is equal to m node, then your magnetization mz as a function of time is equal to m node 1 minus exponent to the power t over t1. So the physical meaning of the longitudinal relaxation time, you just put your vector, you deflect it from the axis z, and then you see how with the time it relaxes back to its value. So this is all what I wanted to tell you about transverse longitudinal magnetization. In principle, this is a sort of kinetic equation, and in order to get this kinetic equation from the microscopic model, one needs to do some calculations based on solution of kinetic equation. I'm not going to do that. Let's now look at the transverse equation. Right. Again, there is a technique for measuring longitudinal relaxation time, and this technique is related to spin echo. For those who are interested in the measurement of the relaxation times in solid state experiments, I recommend the book of White, which I give a reference on the first lecture, Theory of Magnetism, Quantum Theory of Magnetism, where you can read a lot about experiments in magnetic materials. So, transverse equations. Sorry?
Professor?
Yes.
I have a question.
Yes.
Can you maybe please comment, the one you're deriving right now is about the spin dynamics equation, right? So, I want you to maybe comment about the Lindblad-Master equation that's also related to the spin dynamics. You think that's
yes, sure.
different with this one?
This is a sort of kinetic equation, yeah. Lindblad is typically you take some bar, some thermostat, and you define some superoperator. Yeah, this is the same. That's absolutely correct. I'm just emphasizing the difference between transverse and longitudinal components. So while transverse longitudinal component is given by N8 sort of master equation, the transverse one will be related to the oscillator with the friction. What I'm going to show you now is that in the presence of transverse relaxation processes, you will get just harmonic oscillator with the friction. Dissipation. This is dissipation. Okay. The equations. If I write down the equations component by component, let me just do that. dmx over dt, I'm talking about the transverse component, is equal to omega node my minus mx over t2. What is important due to this axial symmetry, that the relaxation times in the transverse direction are the same. So dmy over dt is equal to minus omega node mx plus gamma m node hy t minus my over t2. So these are both equations and transverse part of it. So I do the very same trick. I will take d2 over dt squared mx. It is equal to omega node dmy over dt minus 1 over t2 dmx over dt. Then it is equal to, from the second equation, I write it down as omega node minus omega node mx plus gamma m node hy t minus my, let me write it, my over t2, I wrote this term, minus dmx over dt. So it still contains my, but my I'm getting from this equation. So my is 1 over omega node dmx over dt minus mx over t2. So then it is minus omega node squared mx plus gamma omega node m node h1 minus omega node divided by 2 omega node dmx over dt times 1 over t2 and minus my, so this is plus plus mx over t2 and minus 1 over t2 dmx over dt. Good. I will rewrite it here. So mx double dot plus omega node squared mx. Then I have two terms. Omega node over 2t dmx over dt. Where is factor 2? There is no factor 2. There is no factor 2 here, so I have this term and this term. And they both come with a sign minus, therefore they will come with a sign plus. So this is 2 over t2 dmx over dt. And then I have this term which comes with a sign plus, omega node cancels out. So this is plus mx over t2 squared is equal to gamma omega naught m naught h1 t. So what we see here is, as I said, harmonic oscillator with a friction, and here we have external force. Okay, and this is a friction. This is something which is proportional to velocity in classical mechanics. Again, in linearized form, we got harmonic oscillator. So now we need to construct the green function of this linear differential equation. And let's quickly do that. I deliberately put this part intact. So my linear differential operator LT is now d over dt squared plus 2 over d2 over 2t2 d over dt plus omega naught squared plus 1 over t2 squared. And the equation for green function is L t prime times green function t minus t prime is equal to delta function t minus t prime. I am not going to repeat the full procedure. I do Fourier, and if I do Fourier, what I get? So first of all, omega naught squared plus 1 over t2 squared minus omega squared, and actually minus 2I over t2 omega times g omega is equal to 1. So I do this very same trick. The Fourier transform of the delta function is 1. I plug in Fourier transform of the green function, apply the differential operator to the exponent. You remember there is exponent to the power minus I omega tau. Therefore, my green function g omega is equal to 1 divided by omega naught squared minus omega plus I over t2 squared. Check it. Omega naught squared minus omega squared minus 2 times omega I over t2 plus t2 squared. So you see that in the presence of the transverse relaxation processes, we have our delta equal to 1 over t2. Therefore, with the same level of calculations, this is why I left this delta intact. G retarded, so retardation is achieved automatically. So relaxation actually gives me a shift of the poles of my green function in the right plane, because this is a dissipation. You know, it's equal to sinus omega naught tau divided by omega naught e to the power minus tau divided by t2 and theta function tau. Good. You see that for the same token, I calculated the green function in the presence of the relaxation processes. And last thing which I'm going to comment during next maybe 5 minutes is how the susceptibility looks like. Draw you some picture, and then we will have time for the questions. I also would like to leave this here. Let's discuss the properties susceptibility in the omega frame. So chi xx is equal to gamma omega node and node times g r omega. And g r omega is equal to minus 1/2 omega node, 1/omega minus omega node plus I over T2, minus 1/omega plus omega node plus I over T2. So first of all, imaginary part of the green function. Imaginary part of GR, I multiply it by complex conjugated, and it's equal to gamma chi xx is equal to gamma m node divided by 2T2, and I have a two Lorentz cells. 1/omega minus omega node square plus 1/T2 square minus 1/omega plus omega node square plus 1/T2 square. So, indeed, we see the very same property, that the imaginary part is odd function of the frequency. So if I plot the picture, now we have two Lorentz centered at omega node and minus omega node. The half width of this Lorentz at the half height gives you 1/T2. So this is the width of the Lorentz. Therefore, the same sort of measurement, namely measurement of the imaginary part of susceptibility, gives you not only information about the spectrum, in this case frequency of precession, but it also gives you information of the width of your line, and therefore it gives you information about relaxation. So, the task which I give to you as a homework, I need to join somehow these two Lorentz cells, and if you analyze the behavior of imaginary part of chi xx at omega goes to 0, you can do it directly from this equation. I ask you to show you that this is proportional to omega. So therefore, there is a line like that, and actually the fact that your imaginary part of the function, this is im chi xx, is a function of omega, is linear at small omega, is characteristic for bosonic systems. We will see on Monday that the sessions which I consider now can be understood as sort of optical magnum, the same way as you consider optical phonon. Optical means that the spectrum is gapped. And magnums are bosons. So this is a characteristic of bosonic function, and the same is for plasmons, the same is for photons. This is this one. Do this exercise, this is just algebra, nothing more than that. And for the real part, I will write down the expression. Real part of chi xx is equal to gamma m node divided by 2 times bracket omega node minus omega. Omega node minus omega square plus 1/T2 square plus omega node plus omega node plus omega square plus 1/T2 You can get it from the same general equation. So you see from this that if you replace omega by minus omega, the real part is symmetric, so the real part is even part of the frequency. So I'm not going to draw it, probably like that, so it goes something like that. So it definitely goes down as 1 over omega, for the large omega no, it goes as 1 over omega squared, sorry. As 1 over omega squared. Because the leading term will cancel out. And you see that this is actually principal value of omega naught, 1 over omega naught square minus omega square. So real time x. Omega is principal value of omega naught square minus omega square. So it behaves as 1 minus omega at the both wings. And actually the position of extrema do not coincide with the position of Lorentz and peaks. So you just consider this function and plot the correct picture. This is just schematic cartoon. Again, as a part of your not mandatory homework. So what did we do today? We first of all derived the gyroscope equation describing precession of the magnetization vector subject to time-dependent magnetic field. In the case when there is a small parameter, namely your magnetization slightly deviates from the axis along which the strongest magnetic field is applied, we derived linearized equation and we showed that the motion in the plane perpendicular to the direction of the constant magnetic field is described by harmonic oscillator. This is a precession. We identify the frequency of precession and we construct in the linear response the dynamical susceptibility and showed that the imaginary part of susceptibility is characterized by two delta functional peaks. Then we consider what happens in the presence of dissipation processes. Again, microscopics of these dissipation processes is related to some particular microscopic models. I'm not going to dwell into that, but the gyroscope equations are replaced by the log equations. The dynamics of longitudinal components is related to solution of Maxwell kinetic equation or Lindbergh equation, while the transverse component can be viewed as the oscillator with a frequency. And we have found that the transverse relaxation time can be found from the measurement of the imaginary part of your susceptibility, which gives you the line width. The same way as the position of extremum gives you information about precession. We will continue studying dynamical susceptibility during next 2 lectures on the blackboard, and I will show you more information on how people measure it experimentally using, in particular, neutron scattering or spin echo technique at the very last lecture, which will be summary of superconductivity and magnetism in connection with behavior of strongly correlated systems. That's all. Questions? So you don't have questions. This is bad. So, if you don't have questions, then we meet on Monday and we are going to discuss microscopic model of the ferromagnetism, mainly Ising model and Heisenberg model, and we are going to discuss magnons and behavior of static and dynamic susceptibilities below and above the phase transition point. This is planned for Monday.
Excuse me, sir.
Yes? Yes, please. Yes.
About homework,
Yeah?
could you extend for us maybe like from a few days? I think I will not do that program.
Why do you need that? I think you have almost everything to solve your homework. Let's discuss it on Monday. Because we need to set exam. So when I complete my course, and I hope next Friday we are done with the course, then we need to have 1 or 2 meetings. So at least 1 or 2 meetings. If we are talking about 1 meeting, then in the same meeting we discuss your homework. Therefore, I need to have some time to check it and discuss in details what are the solutions and what are the common problems with this homework. And then we need to discuss the exam and procedure. So the most recent information from the COVID committee is that in-person exams are allowed, so we need also to set the date of exam, in particular either before Easter or after Easter, because we need to discuss it. And I will listen to your suggestions. Or maybe we need to have 2 meetings, therefore 1 meeting will be devoted to the homework, and second meeting will be devoted to the discussion of the whole course. Namely, maybe before exam you accumulated questions about different topics of the course, and I will be happy to provide you some explanations and clarifications for those questions which arise in the time of preparation to exam. So remember that after March 12th, we need to meet either once or twice, because before you have exam, and we need to decide about the date of exam. So far, I think the exam will be written. Last year, it was almost the same period of the year, but students were all, and including myself, not only students, but lecturers, were in a strong lockdown, and I decided that I will take oral exam that time. But I think now we are not at that critical situation. Oral exam means I need to make appointment with each of you personally and question you within like half an hour per person. With the 16th person, you see that this is 8 hours. We will not be able to do it in 1 day. But with the written exam, I think we have a standard 4 hours procedure. We will book the Budinich lecture hall, and those students who are at ACTP will just come in person for the written exam, but other students stay online. So, by Monday, I appreciate if you tell me whether you need extension for homework or not. If it is one person who wants to do it, I'm sorry. If it's, say, half of students who want to do it, we will discuss. Especially, I would like to understand the reason why it is so. Second, I would like to have a suggestion whether we meet once or twice before exam. And third, when I get answer to this question, I will make arrangement with the diploma office for this 1 or 2 meetings. And then your suggestion about exam. In particular, would you prefer to have it before Easter or after Easter? Okay, 3 questions.
Hello?
Yes.
Professor, so about the homework, I already did most of it, I think, but it's still not ordered, so I need to rewrite it. And I think it's more of a, I mean, in my opinion, it's more of a mathematically difficult problems. I don't know if I really learned more physics out of the problem because, yeah, sorry, this is just my selfish opinion.
Look, I'm very happy that you express your personal opinion, but I would also like to have statistics. The group has representative, which is Jonah. You have a weekend to discuss among you all critical whatever comments. I will take it carefully, take it into account, but if I will listen now 16 different opinions, it will take us at least another hour. So I prefer to simplify this procedure and make it efficient. Namely, you discuss it among yourself, you let your representative to express me a cumulative point of view. I will take this point of view, say, by Monday. I will think about your suggestions. I come back to you on Wednesday, and then it's like, democratic majority vote. And therefore, I formulate my questions in a very simple way. If we have a 16 different opinions, not coinciding in gender or whatever, I cannot optimize 16-dimensional, 16 parametric function. But I can easily optimize 2 parametric function and find extremum of this. Okay? So this is why I suggest you to think, to discuss with your friends, and let Yona to present me the collective opinion of the group.
Okay, sir. I will do that, Professor.
Good. Okay, then if there are no more questions, further questions, have a nice weekend, and I see you on Monday next week.